Mode 6 synchronous counter. So we know that in mode 6 counter, like in the case of asynchronous counter, mode 6 synchronous counter also counts from 0 to 5. So 0 to 5 means there are 6 states, that is 0, 1, 2, 3, 4, 5. So there are 6 states. So the last number that it will count will be 101. After 5 it will again repeat to 0 and this will continue. It's a synchronous counter, so all the clocks will be synchronized. Okay, so in a mode 6 synchronous counter you have to design. So how do you design? You have Q2, Q1, Q0, Q2 plus, Q1 plus, Q0 plus. We'll take JK flip-flop. So J2, K2, J1, K1, J0, K0. So the present states will be 0 to 5. So 0, 1, 2, 3, 4, 5, then it will repeat. So 0 next state will be 1, 1 next state will be 2, 2 next state will be 3, 3's next state will be 4, 4 next state will be 5, 5 next state will be 0. So if you see Q2 and Q2 plus and write J2 K2, 0 0 it is 0 don't care, 0 0 it is again 0 don't care, 0 0 0 don't care, 0 1 it is 1 don't care, 1 1 it is don't care 0, 1 0 it is 1 0 it is don't care 1. J1 K1 will get from Q1 and Q1 plus. 0 0 is 0 don't care, 0 1 is 1 don't care, 1 1 is don't care 0, 1 0 is don't care 1, 0 0 is 0 don't care, 0 0 is 0 don't care. J0 0 K0 from Q0 and Q0 plus. 0 1 is 1 don't care, 1 0 is don't care 1, 0 1 is 0 1 is 1 don't care, 1 0 is don't care 1, 0 1 is 1 don't care, this is don't care 1. Okay, so like in the other cases we have to draw the K-map for J2, K2, J1, K1, J0, K0. There will be 6 K-maps. You have to get 6 expressions and then draw the circuit. Now here there are some things which you should see. That is, here we will be drawing the K-map for Q2, Q1, Q0. That is, the variables inside the K-map will be Q2, Q1 and Q0. So it will be a 3 variable K-map. 3 variable K-map means you have 0 to 7 cells inside the K-map. But here we are dealing with only from 0 to 5. So 6 and 7, those two cells we have not dealt with in this particular table. So those you'll be putting don't care. Okay, so in this case J0 K0, if you see, all are either don't care or 1, and 6 and 7 also you will be putting don't care. So you can directly write that J0 is equal to 1 and K0 is equal to 1 because there are no zeros. So J0 equal to K0 equal to, it is 1 itself. So you can write for J2 Q2 Q1 Q0 0 0 0 1 1 1 1 0. This is 0 1. So J2, this is 0 1 2 3. So for 3, then 4 and 5 it's don't care. 4 and 5 it is don't care. 6 and 7 we know it is don't care. Why? Because we have, those are unused states, invalid states. So we are putting don't care there. So here it is like this. So that is Q1 Q0. Okay. And K2 is for K2 it is 0 1 2 3. 0 1 2 3 it is don't care. 4 is 0. 5 is 1. 6 and 7 is don't care. So for this one you can group it like this. So that is Q0. Yes. Then for J1. For J1 it is, you must draw separate K maps. I am drawing like this only because of lack of space. So J1 0 1 1 2 3, then 6 and 7. Okay, so here it is like this. So J1 is Q2 bar Q0. Correct? J1 0 1 2 3 4 5 is not there, 6 7. Okay. Next is K1. For K1 it is K1 0 1 2 3 4 5 6 7. Yes, so it is like this. So that will be Q0. Okay, and J0 K0 is 1. So here there is an issue, that is suppose 6 and 7 are unused states. That is 110 and 111 are new states. We should not go to these two states because in a mod 6 counter it should count only from 0 to 5. After 5 it should return to 0. But in K-map what did we do? We put 6 and 7 as don't care. Don't care means what? It can be 0 or 1. Okay. So suppose in such a case, any such circuit, any synchronous circuit in which there are unused states, that is in this case we had 3 bits. 3 bits means you have 0 to 7, that is 8 states. So if you are not using all the 8 states, if you don't have a result for all the 8 states, either a 0 or a 1, then those states are called unused states. If you have 4 bits, then 0 to 15. Those 16 states, any of them does not come as a valid state in our circuit, then those are unused states or invalid states. So if you have invalid states, any circuit in which there is an invalid state, if an invalid state comes in, because those invalid states we have taken as don't cares. Don't care just means 0 or 1. It can be either. So when you are dealing with a synchronous circuit, if you are drawing the circuit using this and you are continuously giving the clock. So while giving the clock, due to some reason, suppose 6 comes in. Okay. So if 6 comes in, that is wrong, right? But even if that 6 comes in, it's okay. If it is okay if within 1 or 2 clock cycles, it returns to original state, returns to the original cycle. Original cycle means to one of the valid states. Then it's okay. Okay. In between the working of the counter, if an invalid state comes in, it's okay. But within 1 or 2 clock cycles, it should return to the actual sequence. Then it's okay. Then the counter has no issues. But if it does not return, if an invalid state comes in and it does not return to the original state within 1 or 2 clock cycles, then it is called as lockout. That is an issue. So lockout is an issue seen in synchronous counters wherein you have invalid states, and if an invalid state comes in and within 1 or 2 clock cycles it does not return to the original state, then that is called as lockout. For example, in this particular case 6 comes in. I apply a clock pulse, it goes to say 7. I apply another clock pulse, it goes to 6. I apply another clock pulse, it goes to 7. It hangs in these states. Okay, it does not return to the original original sequence of valid states. It is stuck here. So that is called as lockout. Okay, so 2 types of questions will come. One is you'll be given such a question where it can be a mode and counter, or it can be a random sequence generator. In both the cases, you won't be using all the 2 raised to n states if you are using n flip-flops. So in those cases, you'll be asked to check for lockout, and if there is a lockout, then design for lockout. So in the case of invalid states, check for lockout will be a question. And if there is lockout, then design for lockout. That is one type of question. Or you can be asked only to check for lockout. Okay. Second question will be just design a mode 6 synchronous counter or design such and such sequence generator. So we'll talk about both. Okay. So first, since we did so much and we have some equations handy, we'll check for lockout. So how do you check for lockout? These are the equations. So in such a case wherein you are using the invalid states and you are putting the don't care for the invalid state, or you are asked to check for lockout, in such cases you'll be putting the don't care, getting the equations from the K-map. Till here it's like any synchronous circuit design. After that you have to check for lockout. So how do you check for lockout? Lockout means if an invalid state comes in. Invalid state comes in. What happens next? That is the condition for lockout. That is, if an invalid state comes in, within 1 or 2 clock pulses, does it return to the original sequence? In this case, 0 to 5. Okay. So we'll write the invalid states. Here the invalid states are 6 and 7. Yes. And what do we have? We know J2, K2, J1, K1, J0, K0. How do we know that? From the equations. Then we'll check for Q2 plus, Q1 plus, Q0 plus. Okay. So from J2, K2, from this, Q1, Q0 is J2. So we'll take this Q1, Q0, Q1 into Q0. So that is J2. So 1 into 0, 0. Here it is 1 into 1, 1. J2. K2 is Q0. So that is 0 here and 1 here. 0, 1. Likewise, J1, K1. J1 is Q2 bar, Q0. Q2 bar. So that is 0. And here it is J1 is Q2 bar. So this is again 0. K1 is Q0. So this is 0. This is 1. J0, K0 it is 1. Okay. So you know Q2, you know J2, K2. You know Qn, you know J2, K2. You can write Qn plus 1 from truth table. How? So J2, K2 is 0, 0. 0, 0 is Qn. Qn is what? 1. 1, 1 is Qn bar. So that is 0. J1, K1 is 0, 0. So Qn 0, 1 is 0. Q0 plus you'll get from J0, K0. That is 1, 1. 1, 1 is Qn bar. So 0 complement is 1. 1, 1. 1 complement is 0. Now see here, if 6 comes in, after one clock pulse, what do you get? Qn plus 1, that is 7. 6 comes in, yes, an invalid state 6 comes, you apply a clock, it goes to 7. So now 7 is the present state. So if you apply a second clock, what happens? 7. So 7 is now there. You apply another clock pulse, it goes to 0. This is a valid state. So within 2 clock pulse, it returned to the original sequence or a valid state. So this is okay. Or if 6 is not coming, only 7 is coming. So within 1 clock pulse itself, it returns to the original state. So if 6 is coming, 2 clock pulses you will take to return to the original clock pulse, original sequence. If 7 comes in, it goes to the original sequence within 1 clock pulse. So even if an invalid state comes in, it will return to the original sequence. So what do you conclude? There is no lockout. So when there is no lockout, then you needn't design for lockout. You can use these equations itself. Just draw the circuit like you would in any normal synchronous design. So how do you do that? J2, K2, Q2, Q2 bar, J1, K1, Q1, Q1 bar, J0, K0, Q0, Q0 bar. Yes. So J2 is Q1, Q0. Q1, Q0, that is J2. K2 is Q0. J1 is Q2 bar Q0. Sorry, J1 is Q2 bar Q0. Q2 bar Q0. Q2 bar Q0. K1 is Q0. J0, K0 is 1. We'll be taking the LEDs from Q2, Q1 and Q0. I'm not drawing that just to avoid the confusion. Okay, it's understood that you'll be taking the LEDs from output connections from Q2, Q1 and Q0. Okay. So this is mode 6 counter, checking for lockout and drawing the circuit. So here you didn't have a lockout. So we'll also talk about how to draw the timing diagram of a mode and counter. So mode and counter means 2, 3, 4, 5. Okay, one more. Okay. So we are assuming Oh, sorry. In the earlier circuit, you have to draw the synchronous clock also. I forgot that. So don't forget to draw the clock. Because it's a synchronous counter, you have to draw the synchronous clock. That is, all the flip-flops should have same clock. If these are the flip-flops, you should draw like this. Don't forget this. Okay. So I forgot that in the earlier circuit. Don't forget to draw that. So this is clock number 1, 2, 3, 4, 5, 6, 7. So these are the clock pulses. You have Q2, Q1 and Q0. So this negative edge is my first clock. So what comes after that is what is the after the first clock. So initial state will be 0. Then I'll get 1, 2, 3, 4, 5. Again it will go to 0. I'm stopping there. Okay, 5. After 5, it will go to 0 in the case of a synchronous counter. So if it's a synchronous counter, this is the case. Okay. So in the case of asynchronous counter, how did we do a mode and counter? If you used mode 6 counter, 0 to 5 it will count, and 6, that is Q2, Q1, Q0. You'll connect a NAND gate. This will be given to the clear of all the flip-flops, and this you'll connect to Q2 and Q1. So if this becomes 1 and this becomes 1, this will become 0 and all the flip-flops will be cleared. So in the case of an asynchronous mode and counter, what happens is, till here it's the same. After 5, 6 will come, but for a very short duration. It will just come, we won't see it. Okay, just as the 6 comes in, for just a few nanosecond it will come, and then the NAND gate output will become 0 and clear will become active and all the flip-flops will be cleared. So just for a very short duration this will become high. After that it is 0. So after that it becomes 0. It's 0. So here you can see that after the 6th clock pulse it is 1 1 for a very short duration, and later on in the same clock pulse it is going to 0 because the clear is an asynchronous input. So when a clear is applied, it is not waiting for the next clock pulse to get cleared. It will happen whenever the clear gets a 0. So this is asynchronous mode 6. The other one was synchronous mode 6. In synchronous mode 6, we don't have any such thing. We are designing. Okay, the entire circuit is designed, so it will come directly to 0, 0, 0 itself. So that is the difference between a synchronous and an asynchronous counter, mode 6 counter.